We're told that the principal argument of a complex number lies in the interval 0 to 2 pi in this question, so we've got to use that. You cannot, if you're not told it, you can use minus pi to pi instead, but we have to instead always keep it positive. So just a reminder what this actually means. So if I had, say, an argument here, then it's going to be greater than 0, and I kind of just keep increasing it until I get around to here, and it's still positive. The 2 pi is when it kind of gets back to being 0. So that argument, instead of being, say, the minus whatever this angle is, it'll be all the way around there. Just got to be aware of it, but we can deal with it, no problem. We're asked to determine Z1, Z2 to start with. So multiply these two complex numbers together. I'm going to get minus 15 plus 36i minus 20i plus 48i squared, which becomes minus 48. Of course, I squared equals minus 1. That will give me minus 63 plus 16i. In part B, we're asked to express Z2 in modulus argument form. So Z2 is minus 5 plus 12i. That means it's going to be, say, up here, because this is my real axis, this is my imaginary axis. And this distance here is 5, well, it's minus 5, but the length is 5, and this is 12. So we use Pythagoras' theorem to get the magnitude, or the modulus of it. So the magnitude of Z2 will be 5 squared plus 12 squared, square rooted. You might know this is a Pythagorean triple. It gives you 13. If not, just put it in your calculator. Now we want the arguments. For this, I tend to find the acute angle inside the triangle and then add on as needed. So tan theta is going to be 5 over 12. That means theta is going to be inverse tan of 5 over 12, which gives 0.3947. And that means the argument of Z2, I just need to add on pi over 2, this right angled here. Which gives us 1.9655. Now let's write it in modulus argument form. So just very quickly, if I have a complex number that's where x is positive and y is positive, here we go, then I would actually have this, my real amount as x, and my imaginary amount as y. I've got my modulus here, so I'll call it modulus of z. And here is my argument, which I'll just call phi. Then I could say that x is actually the modulus of z cos phi, because you could say that cos phi is the adjacent x divided by the modulus of z, and then just rearrange that. And y is going to be the modulus of z sine phi. Bring that together, because it's x plus iy, gives us that the complex number would equal the modulus of z times cos phi for x, and then plus the modulus of z times sine phi times I for the y part. In fact, you can just factorize the modulus of z out, and you get modulus of z cos phi plus I sine phi. This is our modulus argument form. This actually can be extended for when the argument goes beyond pi over 2 and values become negative. So this is just something to learn, as well as seeing where it comes from. So finally, for us, we've got that Z2 is going to be 13, then cos of 1.97, so I'm rounding to 3 significant figures, plus I sine 1.97. That is our modulus argument form. Finally, verify by direct calculation that when you times two complex numbers together, you essentially add in the arguments from your two original. Okay, well, let's work on the argument of Z1 to start with. We've got the argument of Z2. So for Z1, we have 3 plus 4i. So we can represent it like that, which means the argument of Z1 is going to be inverse tan of 4 over 3. Which gives me 0.9272. And then Z1, Z2. Remember, it's minus 63 plus 16i. So it's over here somewhere. Again, I'm going to work out this angle and then add on pi over 2. So I've got 63 and 16. Inverse tan of 63 over 16 plus pi over 2. That's going to give me my argument. I get 2.8928. So therefore, the argument of Z1 plus the argument of Z2 is going to equal 0.9272 plus 1.9655, which if you put in your calculator will give 2.8928, which is the argument of Z1, Z2. And that is what we're asked to show. So this actually is true in general, but we've shown it for a specific case here. Well done.